My great pleasure to introduce Lennart Bittel from Düsseldorf, a friendly group like run by Martin Fleet, who was a former PhD student here in Berlin. And Lennart will pick up a topic that we heard about this morning in the group meeting, when we heard about Hamiltonian learning. That's in some area you will see the correction, but he will be talking about fast estimation of gradients in variational quantum algorithms. So thanks for coming, and the stage is for you.
Thanks. Hello, everyone. Yeah, I've heard you were from a different topic.
Too late now.
Yeah, no, this is work I did with my doing with my master's student Jens Ratti, Martin Fleet. Yeah, it should be on the archive, I guess, last week, but that didn't work out. So hopefully next week, or we'll see. So yeah, the title is fast estimation of gradients, and in this case, fast means a few measurement rounds. So we just want to have an estimate of a gradient with as little like resources or like time required. So first I will go quickly through all those points. So I will define VQAs. Quite a few of you have been working on those, but for the rest, just a quick introduction. Then I will talk about gradient estimation and the framework that kind of arises from these VQAs. Then I will talk about our Bayesian approach, and then show some numerical results on the end. Yeah, do a conclusion. At any point, if you have questions, ask me. So briefly, what is a VQA? It stands for a variational quantum algorithm. And the simple idea is just that you, depending on what type, but you just have unitaries, which are parameterized by a real value that can somehow be chosen. And then you measure a certain observable value. These unitaries are effectively time evolutions. So they are generated by some generator, which can be thought of as a Hamiltonian. And for the purpose of this talk, in general, we will assume that those unitaries are periodic. So, and if they are periodic, we just, without loss of generality, set it to 2 pi. That's not necessary, but for our calculations, it's kind of is. And the general goal of the VQA is kind of to find an upper bound for the ground state energy, or the smallest eigenvalue of an observable. And the basically nice thing about it is that you can always find an upper bound by just simply measuring the expectation value. So any expectation value is always larger than the smallest eigenvalue. Yeah, so you always have an effective upper bound. But now, obviously, we want the smallest upper bound possible, so we have to minimize this function g. And for this, like these standard approaches are basically used. So gradient descent-based methods or like second-order methods are generally being used. Also, there's quite a topic of natural gradient, which kind of tries to mimic certain properties. But effectively, yeah, you take the derivatives and then go into what the direction that makes the derivative smaller. On the function smaller is roughly all you can do with these types of problems. So there are quite a few challenges, or I mean problems, I guess, if you consider these VQAs. The first one, I think, which is quite big, is that there's an expressibility problem. So in order to be able to approximate the ground states or find the smallest lambda, like this, inequality has to be somewhat tight for at least one angle, which means effectively we need to be able to prepare the ground state within the setup we have. And this is really not that easy because there are Hamiltonians where the ground state is really hard to prepare.
But then to be fair, you want an approximation of the ground state, right? Say in trace norm. It might be much easier to prepare the preparation than the approximation than the true ones.
Sure, I mean we even just want the eigenenergy, right? So yeah. It might work, but I think you can probably construct problems where you will have a large issue here. And yeah, just complexity-wise, we also have these 2 complexity classes. So ground states are in QMA and VQAs and QCMAs. So there's this whole like theoretical question about how well they will perform. What's the C? Classic. Quantum classical Merlin Arthur and quantum Merlin. So, the classic like QMA is the idea you can verify something with a quantum string, while classical QCMA means you can verify something with a quantum computer, but a classical bit stream.
The communication between them.
Okay.
Classical or semi-quantum state.
Yeah, those are the proof of the quantum state in human.
I think potentially there's a technical problem that people can't see like anything up in the first slide maybe.
Really?
This was a messaging slide.
Oh, I see. It does happen sometimes that you're stuck on the first slide.
Okay,
So maybe you're sharing the browser and not the presentation.
Then just don't go full screen.
Just don't go for screen.
Okay.
Where is it?
Yes,
Maybe then briefly go over the slides again so that we can see them.
Yes.
Okay.
What are you doing?
Fixing it.
Oh, it worked.
Oh.
So, the next big or like major problem you could have is local minima, which was for, I guess, Thomas. So you can ask me afterwards. The point is kind of that we will see, we have these Fourier functions, and they will have quite a lot of like small minima, which don't have to be anywhere close to the smallest eigenvalue. So if you do gradient descent, you kind of walk down the smallest path, which means you will be stuck in a minima. And then bad luck. And the last point, which this talk will more focus on, is some phenomena called Barron plateau. And the idea here is that local minima are one problem, but another problem one can have are these plateaus. So if you consider like you do a gradient descent, but the landscape of your cost function just gets really flat, so that the gradient doesn't really show in any direction anymore, you also don't know where to go. So you will always end there. And this is like relevant for quantum mechanics even more because getting the estimates is an observable. Right? So we measure some observable, which means you always have like noise, even if it's just like normal shot noise, like measurement statistics. So we will always only know the function values approximately. And then if the gradient is exponentially small, we basically can't really know in what direction we want to go.
Is there an intuition why this happens?
There is an intuition, the naive idea that if you have these circuits and you just think of them as being random unitaries, what will you end up in the end? A random state? Ideally, even like a close to half random state. And now imagine you have a random state and then apply a unitary to it. What will you get? Probably another random state. And then if you think about the derivative, like if you change from one random state to another random state, the expectation value of the observable will kind of not change because they both are Gaussian distributed around like the statistic.
Oh, so this is a statement about expectation values or functions of the state. No.
I think it's usually about if you randomly initialize the parameters of your model, and whether you then start off with the so that's where there's random.
So that's usually seen as a kind of 2 design or something like an efficiently comparable random state. But then, of course, one can criticize that by saying that you don't want to prepare a random state.
But then to counter that, you can argue that you effectively, I think if you don't have anything random, then you could just do it classically. And like the Hilbert space is large, and you will always be fighting against the Hilbert space dimensions. And going into more and more areas of the Hilbert space means you will have this randomness kind of start leaping in, and this will effectively reduce like the effective. I will get to it a bit more later on. But, yeah. So the big point I want to do here is now if we want to find a gradient, we kind of want to do that as efficiently as possible. So I already mentioned that the measurement budget or the amount of measurement shots we need might really scale poorly and will be a limiting factor. And the gradient is, at least for like gradient descent, one of the hardest components in the entire algorithm.
I mean, there's a narrative of the measurement problem in variation quantum algorithms, right? Which is meant as a joke, but that will mean that it's commonly infeasible. Take as many measurements as you need to reliably estimate the gradient.
Which is So I mean, I just reduce it to one layer. So we will assume that we have a state and one unitary and the observable. All the previous layers are kind of absorbed in the state. And we use a property that unitaries can always be diagonalized. So if we think of a unitary, we can think of its like eigenspaces, and then just like the unit circle evolution of the eigenstate. And since we before decided that the unitaries have to be periodic, we know that these eigenvalues are all just integers. And then we can go into like a free representation. So if we think about what this function will do, it's actually just a Fourier series of all different eigenvalue differences. So it's just a sum of discrete frequencies with all the eigenvalue differences that exist in the problem. Which could be large, but since we kind of restrict ourselves not to periodic ones, will only be a list of a few integers and yeah. So effectively now we have this function ak sine of mu k of x, and we want to for this specific function we now know the structure. We want to find a good estimate for the space.
That's a very stupid question, but maybe I do it now before it gets more stupid in the next round. So the reduced one layer cost function does, because that's your algorithm that you take, that you fix everything and you look at a layer, want to kind of optimize that layer.
Exactly. The idea is we want to find the gradient.
Yeah, well,
we
yeah,
do that by
doing
going
a choice. That's your choice.
exactly. We go by doing this.
Okay, good.
You could probably do it more fancy.
No, that's fine.
There are a lot of like deviations from each other.
When you choose this lambda I, even if you choose other integers, you could still choose them in a pathological way, such that you don't have just a few frequencies that you have exponentially many.
Yes, the idea is just them being integers follows just from being 2 pi periodic, right? So, and then the effectively what I'm saying it's only going to be a few is because the span can't be that large normally, but you would want to have an energy which is kind of fixed. So you can't really have, well, technically you might be able to, but you can't really have exponential. And for the problems we look at, which is just like sums of simple Pauli observables, you also don't have, like you kind of have from all, like if you just look at the total spin Hamiltonian, for instance, then you go from minus the spins to plus the spins, and something like numbers. That's kind of where we come from. Yes. So if we take this framework, the derivative is quite easy. We just have to take these AKs and multiply them by mu k, and we have the derivative. Like the way we did it, we are now interested in the derivative of f of g of theta, which is just the derivative of f position 0. And we just have to figure out all these Fourier coefficients, and we are done. Which, yeah, I mean, obviously, we can do one easy step we will do, which is kind of straightforward, is to think about it as a symmetric projection. So we will only care about this AK term. And what this means in the protocol is if we measure like a bit to the right, we'll also measure equally to the left, and then just take the average. So now we have the small f function, which is just an anti-symmetric projection, and we got rid of the e. One straightforward way on how one can derive an estimator is, for instance, if we just think about the Hamiltonian being a simple sigma x, or like a simple 1 qubit generator. We determine that that all the eigenvalue differences are 0 or 1. 0 has no impact on the anti-symmetric projection. So the function itself will only be just sine of x times some constant. And this constant is just basically the derivative at the point 0, just some simple looking at what a sine function does. And if we then turn this around, we can see that if we measure its x at the function at the point x and minus x, and then divide by 2 sine of x, that we will basically get the estimate for the gradient at 0. And normally what you do is then choose obviously x to be as large, like to choose x so that sine of x is as large as possible. So now we will generalize this. So this was just for 0 and 1. Now we'll assume that we have a wide range of eigenvalue differences. And this means we allow more measurement positions and also different weights. So the naive idea of the algorithm is we have a list of positions we want to measure it. We have a list of weights we want to measure, list of positions we want to measure it, a list of measurements we do at this position, and then we just take a linear combination given by these weights W to have our estimate. So we just have a linear estimator for. And if we think about it, we can also find quite straightforwardly an error model, which gives us, which shows us how well our algorithm performs. And that is just simply the expected square difference between the true derivative and the derivative roots. And if we now plug in the functions, we can add this f of x. So y pi is the measurement results. F of x pi is what it's supposed to be. If we plug all that in, we get those two terms. So we get here the mu k ak is the true derivative, while this Fourier term is what we get from our estimate. And then back we kind of have the difference between the yi squared and f squared. So we have some statistics. And if we now think about the statistical term, well, this is just the y of I are the measurement results, f of x is what it should be. If there's no error in the system, which we might assume, this will just be given by basically short noise, so just the statistics of the measurements. And one further assumption we do, which also is not that restrictive, I think, is that we assume that no matter where we measure, this variance will more or less be the same. So we just assume that the variance we expect from the measurement results will basically be just some constant sigma squared divided by the number of measurements. Which, I mean, for some Hamiltonians might not be the case. It might be position dependent, but especially if you have more fancy strategies about where you need multiple measurements around to get an expectation, it's quite often the case. And then we can already optimize over the measurement budget. So if we assume that this is the true shot noise, then we can get the optimal measurement budget simply by using Lagrange multipliers. And we get that the number of times we measure will just be proportional to the size of the weights we will use in the linear estimation. And by doing that, we can find a term for the statistical error, which is just basically the one norm of the weights divided by our measurement budget.
Very stupid question. What's the order in which things happen here? Because you're saying I measure as often as the relative weight of the coefficient in my linear estimator is, but don't I first have to measure and then afterwards figure out what my linear estimator is based on the data that I measured?
The idea that we start with, like, the linear estimator is all three basically: the positions, the weights, and the number of measurements.
Okay.
And now we basically try to design good linear estimators. And using kind of the first assumption of like shot noise, we can argue that the number of measurements is just proportional to the weights.
Okay.
We can get rid of the measurements and just consider the weights by using this. Then the systematic error. This was a kind of complicated term. And obviously the crucial point here is that for the systematic error, we have the explicit like existence of all those frequencies. And we can't really know the Fourier coefficients of the function, but then we would also know the function. So we kind of need to find a way of thinking about this like still quantitatively. And the naive idea is just to use some like Bayesian prior ideas. So we assume that while we don't know the Fourier values, we know that there won't be a billion, like just like from basic I don't know, prior knowledge or whatever. So we do have some estimates normally, and we want to use that to basically design good algorithms. And what we need to do is effectively, if we look at this, is we need to get this correlation matrix. So how do two Fourier coefficients correlate? And now the question, of course, is what is this ensemble we are thinking about? So it's just the idea of Bayesian. We have a prior distribution, and then we use an update to find the true or to find the new best guess for our distribution. And while it's obviously not really clear, it has some like there's some arguments you can make about this distribution. We already called it like the distribution over theta, because that's what we're working with, right? So we are talking about a gradient over this function space. So yeah, it would be good for an algorithm to perform well on the set of angles we're actually looking at. So this is kind of the obvious idea. And then if we want to make it easier to calculate, we can also just think of it as being an ensemble about over the entire like all possible angles that exist. So all possible theta between 0 and 2 pi. Which seems kind of large and might not work for the relevant ones we're looking at or close to the final state. But for instance, if we think about it, if we start with random initialization, then the starting point is already chosen exactly from this ensemble. Yeah, and
Is this representative of further steps in the optimization?
like I mean that's the next point. Basically, the idea is no, obviously, like
Okay,
will
so
all
you're thinking
depend.
of that.
But the basic point is a bit what you will also see that it doesn't matter if you overestimate, for instance. If you assume that the Fourier coefficients are larger than they actually are, it will turn out that, okay, we are not as good, but we are still better than some alternative approaches. But no, I mean, it won't work, and possibly you could, depending on where you are in the algorithm, optimize all of that. But just as a basic idea, like we will assume those values.
And another maybe not too derailing question, I hope, is that, I mean, when you do the measurement, like natively you get, of course, the gradients, but from the sign cosine features, you also get information about the Hessian of the matrix, like second order information. Like you get some gradient information and some Hessian information in the form of like some vector times the gradient and some Hilbert scalar product between some indicator matrix and the Hessian. That's what you usually get. Is there any value in like using the second order information?
I mean, the goal here is to find the gradient, right? So
No, that's why I fear that would be a bit derailing, because I mean it's known that second order information can improve gradient methods, and that's the information you kind of don't use, right?
okay, so the goal here is just gradient.
Yeah,
I'm
yeah.
pretty sure, like the
No,
argument we're making can
you probably doesn't appear. That's why
the argument we are making, I think, can be generalized to Hessian.
Yeah.
But Hessian, I mean, the naive point is, if you think about what the second derivative is,
Yeah.
it's just dk times mu squared
Yeah, okay.
in some form. So you can get also higher order. We, as you mentioned in the beginning, we are thinking of like just layer by layer.
I see.
You probably can also find something more fancy where you
You like
change multiple layers and multiple points and
Yeah.
optimize the gradient. But
Okay.
this is kind of more the approach of a single layer.
Sorry, how do you quantify the third point?
Numerically. I mean, the like fancy argument, I think, would be something about similar to what happened before about parent plateaus.
Yeah, I think
Like
so.
the Hilbert space is massive, and if you think about it, as long as you have a lot of layers, also the parameter space is massive. And then similar effectively to kind of ergodic arguments and statistical physics. Like in statistical physics, you also make the assumption that every point in phase space is equally likely, and then you calculate whatever happens afterwards. And this is obviously also not the case, but as long as it's large enough, like statistical physics works, and then like, one might argue that here it also works, which I mean, can be false, of course, but yeah, for numerically it seems quite good. Yeah, so what can we get some basic assumptions about those Fourier coefficients? Well, first of all, like we will assume that on average they will be 0. This is not really that hard, I think, to assume. If it wasn't the case, then we would already know in what direction we want to go, effectively. And we will also assume that they are basically not correlated. So this already happens if you just think about like moving one variable from 0 to 2 pi. This integral or this average over all those values will achieve those two sums. Which means that the only question we now have is how do we get those sizes of the Fourier coefficients? And I mean, there are quite a few ideas. One can do like use already existing data and just try to figure out, because you might already know how large it is. You can do kind of simulation of smaller system sizes, which then might hopefully scale. What you can also do is simulate few layers of your VQA, which will always be possible. Scale like complexity on scale to layers, and then add more layers. And this is kind of quite relevant because, as Jens mentioned, if we think about it in the context of many layers, we can actually use like design analysis to find estimates. And the idea is just this, similar to the Baron plateau argument. We will, like, as long as our gates describe kind of a universal gate set, or at least a design, if the layers get large enough, we will basically have this behavior. And you can explicitly, using the design, find find an equation, where the terms like the sigma O is kind of just the average statistical noise you get from the observable. So that's the variance of if you plug in the maximum mixed state. This sum here, like the trace of pi divided by d, is just the likelihood of an eigenvalue existing. So what this entire term is basically just showing is, if you think about the spectrum of your generator, just gives you how likely it is to have that certain energy difference. So this function just says you basically take the variance of your observable, you calculate how often certain eigenvalue differences occur, and then because we are in this design limit, we have this Baron plateau, we divide it by the Hilbert space function. So the barrier, so this formula is surprisingly accurate, but it basically only works in the Baron plateau limit. So for a lot of layers. And now here is just an example from our paper. We basically, so on the x-axis, we have these frequency differences. This is the Hamiltonian up here, just some graph Hamiltonian.
So the large L limit is the Baron plateau limit.
Exactly. So the idea is that with large L, you get the Baron plateau, and this cyan line here plotted is the theoretical Baron plateau limit. So if you see, like, okay, this one point is off, but this point is off with other issues. Like, it is off. I mean, I know why it's off. It's off because this Hamiltonian does not always describe a universal gate set together with the other ones used. And then your Hilbert space is smaller, and therefore such stuff happens. Yeah, it basically, I mean, it really converges to those values, which is not that surprising, but yeah. And we also did that, for instance, in the end, we have some gradient descent plots. This does not really change throughout the optimization. So we can actually converge if we click down enough. The basic statistics of those three coefficients will be like accurately predicted by those values, which kind of like at least numerically points towards that direction.
Sorry, in a very slow at processing plot. So the x-axis is k.
Yeah.
Is that right? And the y-axis is the expected ak squared. Now,
the numerically empirical.
yeah, sorry, the thing you get there. Why is k so like what's the number of qubits here?
16.
Why is k so small?
Well, I mean, it's not small. It will go on until here, I guess.
Oh, you're just not
But
showing
I mean, we're already at 10 to the minus 3.
okay. There would be more cases.
There would be more cases.
Okay. Okay.
So it would go to, I guess, 32. But like it will be like really small. I mean, to be fair, the plot I think is fine to put like this, but the statistic, like this is also sampled over different graphs. So the statistics would be quite cool. I also stopped. I think that's fair. And we also see just in general, I mean, basically showing the Baron plateau, we start again, that the average partial derivative we have is also just decaying exponentially with the system size until it reaches this level. Yeah, this kind of strong or like numerically quite powerful evidence that that there is kind of an underlying distribution that we can actually use because these VQAs will not behave completely gradable. At least like neither as long along our optimization path, nor of course randomly initialized. questions? So, okay, so now we have the full error. We have on the right side, we have a statistical error, which we just give with the short mask. And on the left side, we have this like kind of on prior estimation based guess for the for the kind of systematic error. So the actual mistake we would do even if we measure infinitely. And just add this. And yeah, I mean, this problem is convex in W, which is nice. It's a trigonometric polynomial in X, which makes it a bit more annoying to solve.
But that's because the convex quadratic plus one norm, right? Of course, yeah.
Exactly.
Yeah.
So this is just quadratic and this is one norm.
Yeah.
But the S is kind of this.
The S is nasty, of course. No, in particular, the S depends on X in a funny way.
Exactly. But it's not that hard to solve. The idea we used is to just find a dual with respect to W for some guessed fixed X. And then we can basically get this function G. And if we
So that's you write the Lagrange dual of this guy, and then you kind of guess a solution parameterized by your x's, and then you try to find the matching.
yeah, I mean, what like this has no constraints, right? So I take this equation, add some constraints the way I like, and then find the dual with respect to those constraints, and then this is what the function G is, which is then a convex problem that we can kind of solve. Here, this is like a functional norm or a function norm with big ideas, but by knowing these lambdas, we can then find the optimal x's by having the maximal values of this function. So we can get the points. It's not that hard. Okay, and how do they look? Well, if we now just take a simple example of having mu from 1 to 5 and like an exponentially decaying A. As you saw in the previous plots, we even had this kind of Gaussian decay. Those large values get really small, which is just the effect of having Gaussian concentration in the eigenspace. This exponential is not too extreme and quite probable. Like large eigenvalue differences really happen only seldom. We see that if we start with only a few measurements, we effectively have only one measurement point. So what this plot shows is kind of the optimal x values for each measurement, moving along for like larger and smaller measurement budgets. And here we see the kind of how the error is divided between the statistical error in blue and the systematic error in brown.
Why do you have lots of statistical error for many measurements? Wouldn't you expect it to be the other way around? Shouldn't the statistical error be reduced by
yes, I guess, but the idea is kind of a slight twist. So if we make m really, really small, this means that in relation, the systematic error becomes much more important, which means we will use all our resources to make that 0, which then means that the only thing that remains is the statistical error. Like there's this kind of twist that,
But the statistical error will be much larger and much smaller, like very small. So I don't
like
What you're saying, right?
the issue is kind of this plot is a bit misleading because we have exponential like for with number square root of m, but on the log plot exponentially decreasing errors, right? And the statistical error also gets smaller, but the systematic error just gets quicker smaller than the statistical, which means kind of in the beginning, if we have to do 0 measurements, what our strategy actually does is just return 0. Like, we don't know whether it's positive or negative, and guessing 0 will always be better than guessing and then being more off than you were before. So we kind of have no statistical error because we don't really do any statistics. But if we have all the measurements in the world, then we will find an algorithm where we accurately get the gradient. So where there is no gap between anything. And for this, you actually For this, we call this version unbiased, kind of up here. You actually don't have any like systematic error, which means you also don't need to care about all those prior estimates. We could always run this, and it's effectively just like it's also like analytically solvable. It's just like an like what discrete sign transformation of type 3, I think, which is how you get these weights. So yeah. If we have enough measurements, we will just do that because then we don't have any statistical errors. But if we have very few measurements, doing this is kind of massive overkill. So we get significantly larger statistics. If you look here, we basically have those three options. So SLG, which stands for single linear estimator, is this pink line here. It just basically allows for one single measurement position, which is kind of just a finite differences but smart, like smartly choosing position. And this unbiased is just doing basically those points for every value. We see that like this scales really poorly for small measurements because you have just massive statistical noise. It needs to make the systematic noise small. So yeah, we have
These numbers are pretty terrible. Do you need this?
Yeah.
I mean,
That's
speaking of
the
the
measurement
measurement
problem.
problem.
Yeah, it like the other plot.
Yeah, looks so innocent. I mean,
Yeah, no, I mean that's kind of the issue with that, as you pointed out. Okay, we do know this exact version, which is often quite like used in other contexts. Also, I mean, I don't know whether does VQAs. There's also this product-based generalization. This has exactly the same scaling as with unbiased. So they have the same statistics. So they will have the same plot here. And yeah, if you think about it, even for those kind of reasonably seeming values, in order to like for the unbiased to outperform just returning 0, at least in terms of the like average error, you do already need over 1,000 measurements. So there really is like a measurement problem in that sense, which I mean can be probably fixed or mitigated somehow.
I
But
wanna should maybe also follow up on this, right? Because we have published work on this, as you probably know, and also work in the making with completely different aim, but where this question of how many measurements you need is kind of coming in.
and
Just to make sure that I understand, is the number of measurements here is the overall number of measurements?
yeah. So I mean, yeah, like the 1,000 measurement seems fine, but still, this is just for one layer, one update step. Yeah. And then like the issue is a bit, we are now in this, the point we really don't want to use the 1,000 measurements. So this kind of tells us already two things. Yeah. For once, that this single approach, so just doing one measurement position, just one shot, right, until basically 10 to the 4 in this example. I mean, these numbers are obviously made up, but they closely resemble that like we use in the numeric. Like until 10,000 measurements, the best strategy is just doing a single, like kind of finite differences approach. And only when you go to really like 10 to the 8 measurements, which I guess nobody would do, then it becomes better. So the first result we kind of have is that the smartly chosen finite differences approach will probably be always better. And yeah, now the question is whether we can make that a bit more rigorous, and we can. What we do is we define this omega. So here it was a bit unfair because like the argument was that before 10 to the 3 it would be better to return 0, which is not the case because it probably still has, it's just way too large. So if we would scale it down, it would probably work, but like it doesn't know anything, so it has to be that large. So it just overshoots the size of the gradient by a lot. But maybe from the direction, it's not that bad. And to do that, we can like to figure in a value for all that we kind of have this generalized correlation, which can be seen as just like 1 minus the effective accuracy, which also has this rescaling problem. So it just always is between 0 and 1 and kind of shows the quality of the gradient. With 1 being perfectly accurate and 0 being, of course, showing orthogonally to Let's see. Well, yeah, being not correlated at all, I guess that's the thing. And if we plot this for the values we've chosen, we can see here that the orange line, so the single measurement, basically doesn't really show. And the reason is just that, yeah, as we mentioned, at 10 to the 4 is the only point where they start to deviate, where we actually have a second point in our measurements, where we start doing something a bit more fancy than just finding one. And at 10 to the 4, the gradient quality is already at like 99%. So only in the small region between like 99.6% and 1% and 100% of gradient quality do we get the benefit of using all those fancy kind of.
But this is a pretty tiny benefit.
Exactly.
A pretty funny regime at how many measurements? Pretty many, right?
Between 100,000 and 10 million.
Yeah, I'm not being critical.
I mean, the like you can get a factor of 10 by choosing different sigmas or something, but they are quite large. Yeah. And we can also, like we did a theorem about that. We can show that this is always the case. So it doesn't matter what distribution we use. We do have to assume that the distribution we chose is correct. So there's this small caveat. But if we assume that, then the kind of single shot will always be within 1% accuracy of the unbiased one, of the kind of fancy. We don't have any statistical error. So it really kind of shows that yeah, finite differences kind of wins out in terms of like practical use, just because of those large numbers. Yeah, okay, I mean, I guess now I'm showing you the model I've been using the entire time.
What the theorem? So does this mean that essentially like you can find in your framework you can find a method that shifts this advantage to lower number of measurements? Am I interpreting this correctly?
I can find very shifted to lower measurements. I like by just making the statistical noise smaller. But like if I just make sigma smaller, then n becomes equally smaller, right? So there's this correspondence.
Okay, but sigma you don't have control over it.
Exactly, but it was also get to be one. So
no, I'm just wondering, can you improve the method so that you get the advantage at an earlier point? Is it thinkable that there's an improvement of the method so that you get?
Yes, but the theorem is more like that. Even if it's at an earlier point, the real benefit, assuming that we do know the kind of prior stuff, is at best 1%. Like the scaling of the measurement will change of the x-axis, but it only being this tiny regime up there will basically never change. That's what we understand. So yeah, just which again then kind of means probably we did a bit of an overkill for our entire previous method. We don't really need to know all the Fourier coefficients, but we only need to know the position where we do the single measurement. But yeah. Okay, so now for the numeric model we use, I don't know, anybody who's seen DQA probably saw it. The idea is kind of to have this QAOA approach where you start in the ground state of one Hamiltonian and you go into another one, and then alternating you apply them. Yeah, it's just our numerical example. And what you can see here, these two plots are basically the ones we had before, which were kind of the theory side. Now, like using actual numerical data and statistical sampling of like actual measurement results for I think like 18 qubits. And we see that this is basically the same as we had before. There's like a technicality where the screen is going up, but it's also not that important. And then we also have this R value, which is closely related to omega. But now we kind of have a more like useful interpretation for this omega. Because if we think about it, if we think about gradient descent, we want to find the direction where the function gets smaller. So if and what this R value is, we kind of correlated here. It is the overlap between those two. And it's also if we go, okay, those two have to be normalized. But, if we go into like the normal direction that the gradient estimator gives versus the best gradient, the relation of how fast we will drop down is basically this value R, which then kind of shows why this actually matters, right? Because now we all we want in gradient descent is to always go kind of downhill. And if we think about it at like 1,000 measurements, now 1,000 measurements for the entire gradient, so it's not that preposterous. There's like 12 layers and quite a bit more. We have like the direction of 0.2. So we're going downhill by 20% of what would be ideally possible in the kind of simple finite differences and foundation approach. But for this exact, like no statistical, no systematic error approach, we are actually at basically zero. So we just have a random gradient at this point, meaning that gradient descent won't really work. And to reach this 20%, we do actually need like an order of magnitude more measurements in this other scheme. So it really does affect the kind of budget, right? So it would literally take it like 10 times as long to find the same gradient accuracy. And then yeah, just finally some gradient descent results. It's a bit tricky because they give vastly different areas. We just use like a gradient descent that uses a line search afterwards to like eliminate the kind of different sizes of the gradient.
I didn't get this. What is this?
Now this is the gradient descent plot of the previous one. So this is the cost function on the y-axis. And just after how many iteration rounds we have what value. And then here's kind of the perfect line, what we would get if we didn't have any gradient errors. And then those two are the lines we get either by using the single or like this Bayesian protocol we proposed versus kind of the standard PSR generalization in red, and the this unbiased version we had.
Okay.
And there we see kind of this massive, or this effectively quite massive difference in how many optimization rounds we will also. Yeah. The R, you can interpret it as the cosine between the two. But this term here, if you think about it, is the same as the cosine between the two gradients. Just think back to geometry. This is the cosine.
I think,
so it basically, it just tells you how, like, gradient is the direction where you go the quickest down, like with respect to like Euclidean norm. And this kind of shows you how far off you are. So if it's zero, you're kind of orthogonal to the way you should go. And idea. So okay, my conclusion. Basically, I mean, the kind of using this Bayesian framework while being a bit like maybe not that well defined has this potential of just saving a lot of measurements rounds if you actually go down to it. So in some form, it really does improve gradient quality. Also, what we've shown is that it's probably too fancy to use, but it just gives us a strong indication that using finite differences over trying to really accurately find the exact gradient will always be better for practical purposes. And then some future points we can do. What I mentioned in the beginning, this analysis only works for periodic unitaries. I'm pretty sure you can just generalize it to non-periodic unitaries. The reason why we didn't is more that
what is the non-periodic unitary? I mean, instead of the parameter of the parameterized circuits, right? So in this sense, will unit always be periodic in one way or the other? I mean, what is a non-periodic?
This is more this question about like the eigenvalues of the unitary.
Okay, sorry. Yeah, then
I assume that those are integers.
Okay.
I'm like it probably like at least for it seems quite natural how you can extend the kind of finite differences approach to non-periodic ones. It's not really clear how you can get it or I guess impossible to have the without any statistical error. So if you have like kind of exponentially many different eigenvalues, all with different values, it will be really hard to design an exact estimator. But since we kind of shown that the finite differences approach is quite well, I think that should be easily doable. And the final point, I mean, the issue was a bit what we also mostly worked on was kind of this idea about this plateau convergence of the coefficients. And it does seem like, at least in quite a few cases we looked at, that there's a bit more going on. So you do have, like you can see here that it kind of drops from the structure of the first layer to the barren plateau limit by always going down. So I think you do have some different concentration effects on different like times or like layer depth in the circuit, which as far as I know hasn't really been explored, but would actually be relevant for this at least for those parameters, and I think also in general to understand how much this barren plateau thing really emerges. Yep. And with that will be the end of my report.
Thanks, very nice, that's great. Yeah.
I'm wondering, so this, I don't entirely get this conclusion that finite differences is like, or it's hard to read. Like, where is that coming from? Is that coming from the fact that you with finite differences, you make two shifts essentially, or you can even only make one shift. You measure, and then you already get an estimate for the gradient, and if your shift is small, and I mean, your function would have a smooth relative. It's a good estimate. But then you could do the same thing using a non-effective rule. I mean, obviously, when you have operators in your like that generates your unitaries, then you with the full parameter shift rule, you need to make many measurements, like and many different shifts. But principally, you can sample these shifts, and you can go back to really just sampling 1 or 2 points. So I'm wondering that would that approach be similar in performance to the finite difference?
Okay, first maybe quickly here the issue a bit why like this unbiased here that I proposed, or I mean that I think that is already known. It has the effect, right? So these red flag shows the color of the waves. So if you think about it at low measurement, it basically measures at the correct position, but with the opposite sign. So it uses both sides of the wave to kind of figure out where different frequencies behave, and that's kind of what like just increases the statistics, right? So we basically measure here for the wrong direction, because we also measure here more, and then this kind of cancels out, and we get the accurate numerical result. But but just from the statistics, we basically just measure more and more. So, and just think about these kind of this generator base using the chain rule.
Yeah.
PSR. Okay, I don't have it here. If you simply do the calculation, you have, I don't know, n terms.
Yeah.
And each of those terms basically has a statistical error.
Yeah.
And therefore you subdivide your entire set of measurements in m you subdivide your entire set of measurements in n measurements. So the effective measurements for each is 1 over n, m over n. And then you get statistics, and they also all add up. So you basically get this n squared coefficient, which is then rescaled by the spectral width of each operator, or by the coefficient of the. And if you do all those calculations, you basically, I mean, I didn't show that slide, maybe I should have. The scaling you have here is just sigma squared divided by the spectral width of the system divided by n. This is what we see here, just plainly effectively. And that's also if you do the calculation and assume that the one state for each of these generators is possible, you will basically get the exact same result. So yeah, this green line is just what you get if you do it unbiased. And these two lines, what they do is kind of they use the approach that the eigenvalues concentrate around like a specific value. That if you have like a set of Pauli operators, if you have like this, if you just think about like the simple sigma x, how do these eigenvalues look? They don't look like uniformly distributed between minus n and n, but they really concentrate around like 0, -1, and 1. And therefore the eigendifferences also really like concentrate in that region.
Yeah.
And that means we don't care about the spectral width effectively, but what we do care about more, and which is where this benefit comes from, is we care about this effective spectral width, which is kind of like the spectral width, like, okay, it gets a bit more complicated, but the idea is kind of the average between two eigenvalues, not the extreme.
Can I follow up on this question? We have a nitty-gritty question and a very broad question. The nitty-gritty was following up on this, namely its effective spectral width often seems to have something to say about the times one should pick in the Hamiltonian learning that we talked about earlier today, right? Then you can give some guidance on how far you should go, because we are too short, then you do this polynomial estimation that's clearly not to put in the sample complexity. Very long times are anyway forbidden for time evolution being complete and so on, but a good choice for the intermediate times could also be coming from that. So that's I want to hear your opinion on this. And the broad question is, what's your parental advice? I mean, so you give the advice to the world that you should use Bayesian estimation and do that, right? And the data you take is pretty similar anyway. So yeah, your gospel is do that and don't do anything ever again. Is that right? And if so, I mean, there was by the Zapata people, there was a bit of a Bayesian paper some time ago where they said they made also claims that Bayesian estimators should work better. How does your work relate to that work? I have to look it up, who the authors are again. But that's a very different question, or actually three questions.
I mean, the first one is probably similar, like, I mean, I'm interested in finding the kind of dependence on time evolution over like kind of how large the theta is in the exponent.
Indeed, because that might be something to look at. This might give guidance on what time to pick.
And
yeah, the second one, I mean, I'm not going to mention this. But it basically arose from like a master project where someone was working on the Hamiltonians and kind of used the parameter shift rule, and then was like this other stuff works better.
Yeah.
So yeah, like I think that this measurement problem is like worse than
I mean, I'll do something about it.
like
many people in the group think about this as well, many neighbors and so on.
Yes. I'll do something about it.
and I mean the big point that
Exactly.
I think from the kind of theoretical point of view, I think it's more that the question, like, I mean, like all three of those problems, I think are really like relevant if we like are honest about kind of the Anders classes.
Yeah.
So the first two are somewhat more straightforward, I think, because you kind of know how they behave. While I'm also like, I'm not really sure what these Barron plateau phenomena really mean, because they don't really appear in like classical algorithms, or I mean, they do appear in classical algorithms, but the problem of them is not as bad because you don't have the statistical nature.
Right, so because I mean the variation landscape looks quite similar, right? I mean, like a neural network is kind of similar, but you're saying you don't have the measurements.
Exactly.
Statistics.
Yeah. You don't really have the problem, and I mean in machine learning they always just argue it's good enough for like some stuff you can do, and you can still converge to things, which doesn't really seem to work that well in quantum mechanics because of that measurement issue. Yeah. So I'm not like, but I would be more interested in kind of asking whether this has also some, because there is kind of this big difference, right? In like the probabilistic nature of like quantum computers is also what differentiates it from PP, right? So complexity wise.
Yeah.
Being they're able to only know stuff approximately is kind of essential for quantum computers.
Yeah.
Or to have it. And whether this kind of in reverse has also a role in like P. Yes, I think that's kind of from the theoretical side quite an interesting question. From the practical side, I think you need to, like, if you want to scale stuff up, you will need to more useful structures and avoid this whole plateau regime.
Okay.
And also, I mean, I've been talking to people, and it seems like parent plateaus are not so much of a problem. I mean, for example, Simon here, he has like a gadget for getting rid of parent plateaus by making like global Hamiltonians local, which is kind of nice. I mean, maybe you guys should also talk at some point. And otherwise, I will also talk to David, who you cited, alone. And I mean, visualize like not all over the place, but like one particular region, if you have some kind of information that you want to exploit, then usually you don't run into the character regions. I mean, I think the issue there is a bit like, do we know whether we delay it or whether we actually avoid it? And I mean, just basically, right, all these plots we did are 22. And I mean, okay, the question of whether it's like this plot tries to solve a max-cut problem, right? Max-cut with 22 qubits is pointless. You can always solve it in like milliseconds. But if you would actually think about scaling it up, right, like then any mitigation technique, I think, will just run fundamentally into this Hamiltonian, this silver space will just get massive. So if you argue, hey, if I do these and these mitigation techniques, it works for 20, 30 qubits, I like don't really see how you can like prevent this kind of intrinsic fundamental question of we want to explore a large set of the Hilbert space, but if we explore a large set of the Hilbert space, we will kind of get like noisily, like weirdly into it. And if we do that, then like all the cost functions kind of flatten. And I think that's something that at least I haven't seen a good argument of being really avoidable. I mean, actually, we have like some draw, so like initializing various algorithms lying around that we can chat about some of it is.
Yeah. Oh, that's fun.
One thing I was a bit confused about is that you make Bayesian estimator not so much better than the finite regions approach. But in the last plots that you showed, where the gradient then it seemed that it was actually working significantly better.
It's like the issues. Okay, the issue is a bit that if you look at this plot, here, the point where we actually add a second, like those values are basically on the values we use for being numerics as well. We need 10 to the 4 measurements, so 10,000 measurements for one gradient distance in order to only have even 2 points. So I think for the right one we chose quite a high number of measurements, but for the left one, single and Bayesian are the same because they both have only one measurement point, because single because it can only have one, and Bayesian because that's still the best to do. So those two lines are actually, like you can probably see it, those two lines are like the same down here. And then the unbiased one, which is kind of this discrete sign transform, and this multiplicative PSR are both those two lines which are up here. So,
Okay, the single point line is actually unbelievable.
exactly. Yeah.
Okay, I thought it was. Then I read the.
Yeah.
Wonderful. I think there's a lot to discuss further. Maybe we should kind of close the official part and thank the speaker again for this wonderful talk, and then we have the informal discussion in many constellations. Thanks again.